Okay, so maybe we should start. I don't know if you've seen this announcement, but this week will be only lecture. So it's lecture today and also Thursday. This is so it will cover enough topics to run lab 2. So it's an idea to do it that way and not the other way around. So yeah, today we'll start off talking about the OpenGL pipeline. First some history around it, and then what it's all about, how you program it, and those sort of things. Basically, this will cover these two topics in the course content, so 3D graphics pipeline and data representations. Now, this talk is quite important, but it's also quite dense, unfortunately, so I will try to go a bit fast on not so important things and focus maybe on the technicalities that you will need to learn. Okay, yeah, so in the first lecture I talked a little bit about the pipeline, basically. And I'll just repeat very briefly here what that was about. You will see several diagrams later that gets back to it, so if you can't hang on to this, then you will see it later again. So you have some model that you want to render, and you do that by composing it of system primitives, which in OpenGL is basically point lines and triangles, or varieties of them. Then of course you have a scene in which you have these models in, so you have composition of these models in 2D or 3-dimensional space. Then you have the rendering process, which is basically the conversion process from this 3D, 2D continuous world onto the rasterized discrete grid, which represents your screen, basically. And behind all this is basically the graphics pipeline running. So all the processing step towards this conversion is basically there. It says potentially manipulable. Not all these pipelines are manipulable, but the ones we will look into, the OpenGL pipeline, you have the possibility to manipulate parts of it, and that's sort of what this course is a bit about. Okay. So just briefly some history. I will go quite fast through this. If you want to read more, you have the slides and you can go and look these things up. But basically, in the old days, you didn't really have that much processing power, so you had to find different tricks of making things appear like 3D. So basically, you had to draw things in a way in 2D so that you got to the perception of depth. And that you could do by, for example, if you put remote lines behind here as thin and wide lines, and then you make them thicker and shorter the closer you get to the view, you will get this impression that it's 3D, but it's not really 3D. But I mean, at that time, that was really fancy stuff. But of course, today this is not very impressive. And then you get this availability of dedicated graphics processing, graphics cards, more powerful GPUs, so on and so forth. And then these graphic packages started to try to fill these demands. So something is called render C for graphics application. Some high-level shading languages and so on and so forth started to appear. Yeah, many of these languages have some historical influence. I won't go into details on this image, but sort of general purpose languages over here, and graphics application programming interfaces over here, and shading languages over there. Shading language is basically a way of programming shaders, which I will get back to later. So there's an influence between many of these ones, so you'll probably recognize some of these languages. One I will focus on is basically OpenGL, which lies up here, which is sort of derived from what is called IRIS-GL. Okay, so the roots of OpenGL basically is IRIS-GL. It was an API for a Silicon graphics workstation. It was a proprietary thing, so it didn't have any formal specification. It wasn't sort of like open for everyone to use. So the idea was that when the demand came back in 1992, actually, back in 1992, they took a cross-platform subset of this IRIS-GL and made it into an open graphics library. Of course, in 1992, most people didn't have computers who were able to do this, so there were just some special designated computers where you could actually do this graphics programming. I mean, this was even before the Pentium processor was launched, so it's quite old. And then you had some incremental addition to this cross-platform subset over the years. So there have been many iterations, version 1, 2, 3, and now we're up to 4.6. Version 1 was basically a simple fixed function pipeline, meaning that you really didn't have much possibilities for programming. You could tweak some certain parameters to change things in your manner, but it was not very flexible. So in version 2.2, or 2.0, they introduced programming pipeline, which I will show just in a little while, to give more flexibility to the programmer to do certain things. And the programming is basically due through what's called shaders. Version 3, then they started to remove certain outdated features, like parts of the fixed function pipeline was thrown out. They also took in requirements to deal with transformations, texture mapping, and those sort of things that came along as the graphics program became more advanced and possibilities were increasing. Okay, so just briefly what OpenGL does and does not do. It's a medium level API. Does that tell you anything? Basically, it hides the differences among different platforms and different hardware from different vendors, but it gives you some access to it as well. So it's a bit like C in a sense as a language. It's not completely high level, but it's not low level either, because on low level you have to deal with these different intricacies of different hardware platforms and so on and so forth. Its specialization is rendering effects, high performance, as well as its hardware independence, which is very important, I think, also for this course, that you don't have to really care so much about what platform you run on. You basically have this standard of coding for every platform. It has also been reasonably stable, and it has a concise functionality, and it operates on medium level of complexity, basically. Very briefly about that. Okay, a little bit about this. This is a group, a non-profit consortium that's dedicated to open graphics and parallel computing standards. So, for example, every standard that comes out in connection with OpenGL is connected to this group. And they will basically manage specification of those sort of things. Basically consisting, it was founded in 2000 by a set of quite large companies. And they had some output for the years. Among them, back in the 90s, was OpenGL. Then in 2005 came OpenGL for safety critical graphics, which means for military or medical use. And then lately they introduced Vulkan, which is sort of like a low-level graphics programming framework for high efficiency. So everything connected to this comes out from this group. Every time a new specification shows up, it's basically through this group here. And you'll find a lot of information on their web pages, basically. Okay, so a little bit about the version history of OpenGL. The fixed function pipeline, was all the way from 1992 actually up until 2003, so they operated with that for quite a long time. And then they started to introduce a programming pipeline back in 2004 with Vertex and fragment shaders first and foremost. And then they had this core profile in which they remove outdated features and try to stay up to date with modern standard computer graphics. But they still also keep this legacy, which is sort of like backwards compatible. But that's usually for special interests or special cases. We will not deal with that. We will deal with the core profile here. It's a bit outdated. You see 4.3 there, 4.5 I think came in 2014, and then recently 4.6 came out. So that one should probably have been updated, but anyway. Okay, so I'll start to go a little bit more into details on these things. So I'll start off with the pipeline of OpenGL 2.0. I'll skip to 1.01 because we're not really interested in fixed function pipelines anymore. So basically what you have is a set of vertices. You already seen this in lab 1 when you created this triangle. You created 3 vertices basically. And then you input them into the vertex shader to sort of lay them out in space. And then you generate some primitives, which is OpenGL. As I said before, it's point lines and triangles. This is a means of interpolating in between these points. And once you sort of describe your model with primitives, you rasterize, which is the mapping from your 3-dimensional continuous or 2-dimensional continuous world down to this this grid, which is your screen. Then, or you, in a sense, you say you fragment your model basically, and fragments here refers to pixels. So you will often see this one, which is called pixel shader here, is actually called fragment shader. But I call it pixel shader, obviously, in this version of OpenGL. And then you have some testing mixing, and then you put things into the frame buffer, which basically enable it to be put onto the screen. So the programmable part of this pipeline is the vertex shader and the fragment shader, which they call pixel shader here, but it's the same thing. So before I move on, I will talk a little bit more about what the shader is, because I will mention that many times. It's okay to have a model in your head of what I mean. So basically, a shader is a mini program that you use to reprogram the pipeline. And it basically tells OpenGL how to draw and define a style of rendering, basically. So we saw that with the triangle in Lab 1. It was a very, very simple thing, but you know, start was there. We didn't even deal with colors, so it just dealt with the geometry, the layout. Now, the advantage of shaders is that they utilize the parallel processing capabilities of the GPU. I'll get back to that on the next slide. So you saw in this OpenGL 2.0 pipeline, you have the vertex shader and the fragment shader over here, which you can program. And the vertex shader, you basically, in a sense, already dealt with. It's about positioning each vertex, but also changing them over time, like, for example, moving them with the keyboard and those sort of things. So that you do in the vertex shader. Then you have the fragment shader. It's basically about coloring each fragment of your rasterized model. And that's why it's on the output of the rasterizer here. So you basically color each pixel, or fragment as they call it, which basically refers to a pixel-sized area of the surface. And then you have one shader actually running per vertex or fragment on the screen. So an example here, if you want to render this cube, and your primitives are triangles, you will have 36 vertices. And then basically you will run 36 vertex shaders in parallel. And this is of course much more efficient than doing this sequentially, because now you can do much more interesting things and more heavy things without killing your computer basically. Same with the fragment shader. When you want to color these pixels shown by these squares here, you basically run one fragment shader per pixel. So it's a way of making things more efficient. Any questions on this? Okay. Yeah, so I basically said most of this thing, and this summarizes the OpenGL 2.0. So the yellow blocks here are fixed function blocks, and you can program the ones in gray. The vertex shader is actually obligatory to make it into space, or else it's really no point. The fragment shader is optional because you don't necessarily have to color your object. Put with this step in these diagrams. Talked about that. You went on 0. You basically, well, first of all, you threw away some out the camera then. You will see the slides on the screen anyway. Okay. Yeah, so you do the same with vertex buffer objects, but now you have these GL gen buffers and GL bind buffers. And again, you have the number of arrays you want to generate. So if you want to generate 5, you put 5 there. And then you have an identifier, just like for the array objects. And this one you refer to every time you want to do something about that particular buffer. And then you bind in the same way. You refer to your idea. Only difference is that you have to specify a target. And you have many different buffers in OpenGL. For now we will use array buffers, so you just have to specify a GL array buffer here as the target of this. And then you will refer to the idea every time you want to bind it. Yeah.
If we have more than one vertex buffer, do we have to give a reference to like an array of them, or just keep putting parameters one after the other?
You have to bind them one at a time, basically.
Oh. But not like if you're binding three of them.
No, you can only bind one at a time.
I mean generate them.
Oh yeah, generate. Yeah, sure. Yeah. Then you have to make. Oh yeah. Yeah, then I guess it. Yeah, if you generate several, then probably you will have. Yeah, they will all be bound. Yeah, that's the only because the only way you can bound it is through this idea, basically.
So they share the same idea.
Yeah, I find it a bit strange actually, because then you would have to. How would you separate them? I'll get back to that in the next. I can get back to that in the next lecture after the break, because I hadn't really thought about that thing. But yeah, because it should basically be one identifier per, or maybe you refer to all three of them. That doesn't really make much sense. Yeah, I'll get back to that. Okay. Yeah, so as I say here, unbinding is usually not necessary, because when you bind one, the others are unbound. Okay, so to how you basically can lay out these buffers. So there are three main ways basically on how you can put your data into it. So here I take one example of position and color. Now we haven't input colors yet, because on the first lab we basically changed the background color, and that's not really associated to the vertices. Now we associate colors to the vertices. That makes it possible to color the object itself, like coloring the triangle, which I will show one example later. So for example, you could make one buffer object for all positions. So you put in the positions for the first vertex, you put in the positions for the second and the third, and so on and so forth. And then you have the second buffer in which you put in colors. So RGB1, RGB2, RGB3, and so on and so forth. I made an example from Lab 1, because I don't know if you saw the message, but Carl wrote a extension on Lab 1 using shaders. And the reason for that was that some people got different color triangles on their computers. Someone got the white on this dark rose background, some got a black, I think, and then some were unlucky enough to get the same color as the background, so no matter what they drew, they didn't see anything at all. And that's because you hadn't really told OpenGL which sort of color you want, and then depending on the driver, it may just set something. So he wrote these shaders, and you can play a little bit around with that code. It's now lying on this online here. You can basically download it from here. It's main with shader. Now in this one you can play a little bit around with also the fragment shader, because he's implemented that there. And I will show one example later where I actually do this exact division, just to show how you do that one. So you may put each attribute in one vertex buffer object. That's a bit wasteful in a sense, because since you have to bind and unbind the one you use at any given time, it will kill a lot of resources. Yeah.
So, for example, if we have 3 vertices, so that makes a triangle.
Yep.
And we specify a color for each vertex.
Yep.
How will the triangle get its color, this area?
I'll get to that. I will show an example towards the end, because that's very essential, exactly how you get it. So you may imagine what happens if you put them all to the same color, right?
Yeah.
Okay.
Probably the triangle will have that color.
Yes, exactly. So what happens if they have different colors? I'll show an example. Another way of putting up the buffer is that you have all the position coordinates first, and then you have all the color coordinates at the end. The advantage of this is that you now deal with only one buffer, so you only have to bind one buffer for that particular object. The problem is if you have a lot of attributes and this vertex buffer object is very long, then if you read positions at any given time, then all the other slots are basically taken, so you can't use them for anything else. So that's also a bit of a waste of resources in a sense. But I'll get back to maybe ideas on how you should put this up later and why you should do one thing or the other. The third one is that you interleave the data. So you take the positions for the first vertex, followed by its colors, and then the position of the next one, followed by its colors, and so on and so forth. That's a third way of doing it. And it's a bit more complicated when you put up the pointers that refers to attributes, because you have to tell OpenGL where you find the different things. Now in the first case it's very easy, because the pointer just points to the first, the pointer that deals with position only points to the first buffer object, the one dealing with colors points to the second. In this case you will have to sort of set one pointer that reads from here to here, and another one that reads from there to there. This is the configuration you will use in lab 2, so you'll get an example of that there. The reason for interleaving is a bit fussy. It's really unknown what it gives you as advantages. It's maybe more about how you collect the data in a way. So we have all data connected to one vertex just coming after each other, for example. It's more like a way of choice. Yeah, so I'll just wrap up before I continue with this buffer layout business, or before we take a break. Now it's not convenient to have too many vertex buffer objects to bind and unbind at any given time, because it's quite resource demanding. So for example, if you have one object, you may create one buffer object and then put all its attributes in that one. Another object, you may create another buffer object, and so on and so forth. Then I mean geometrical object in space. If you create only one and you have a lot of attributes, or it gets too long, as I said, space occupied by objects not modified at any given time, it's basically not usable for anything. So you basically occupy the space without using it. So we have to find some sort of trade-off from this. And the problem is that the optimal layout here depends on both your GPU and your driver, so it's a bit of a trial and error thing.
What did you say about the having only one VBO? What did you say about having only one vertex buffer object? How does that occupy space objects not modified at any given time?
Now let's say you put all your data into just one buffer object that is extremely long, and then you want to read positions which is laying from here to here, right?
Yeah.
And all of that space is still just occupied, right, for nothing. So that's why there's no point in dealing with very short vertex buffer objects, but making it too long is not too good either. That's basically the rule of thumb. Okay, I think we can take a break before I continue. So we'll start again in 15 minutes.